Hello, AP Statistics. This is section 9.3, one sample t-test for population means. You're going to need a graphing calculator, paper, pencil, and note sheet I gave you. And once you got those things, you'll be ready to go. All right, I'm going to talk for a second about 9.2. You're like, why are you doing that? 9.2 is very similar to 9.3. The only difference is that at 9.2, we're talking about population proportions. Okay, and there were claims about population proportions that we tested to see whether we believe them to be true or not. And 9.3 is exactly the same, except that we're talking about population means. Okay, we agree that in either sense, it's very difficult to find data on population parameters because, again, populations are so big. And if they're that big, it's hard to collect information from all of them, all the members within the population, and then further come up with a calculation regarding those populations, okay? So what we do is we test it, okay? We use small samples using a p-hat in 9.2 or maybe an x-bar in 9.3 and compare our x-bars, okay, in this sense, to our mu or our p-hat with our p, okay, to see if they are statistically significantly different from what the original claim is with the parameter, okay? And sometimes they are, and sometimes they are not. Okay, but that is what we're going to do in this section. Except that dealing with population proportions, we're going to do with population means. Okay, again, because these kind of in general are very difficult to find. Okay, further, if the population mean is hard to find, then oftentimes the population standard deviation is also difficult to find and is often unknown. Why is it unknown? Well, in order to know the standard deviation, you have to know the population mean, okay? And if you don't know the population mean, then this is impossible to figure out, okay? Further, if in fact I did know this, if I really did know the population mean, the population standard deviation here, that would mean the mean was true, okay? Because if the population standard deviation is true, okay, the only way we could have found that is through a formula using that respective mean. Okay, so again, usually this is unknown, and if it is unknown, like it is in this respective section, then we are not using a z, we will use a t distribution, okay, based off degrees of freedom. So let's get started. And I'm looking at this bottom website here one day, and this website gave a pretty interesting claim. They said that the average distance that a paper airplane could fly is 7 feet. Okay, and I don't know how they came up with an average, okay, a population average, but one of my hours, my fourth hour, was convinced that that may not be true. Okay, so this paragraph starts like this. It says, it is stated that the average distance that a paper airplane can fly is 7 feet. One specific class, which is my fourth hour, believes the average length to be longer and wishes to test the theory. Okay, so what did they each do? They each created an airplane, paper airplane, and they would throw the airplane in the hallway, measuring the number of feet it traveled, okay, before it hit the ground. So once it hit the ground, that was the distance they measured in feet, okay? If it slid a little bit further, that was not part of the measurement, okay? They then marked their distance on a piece of paper, okay? Again, rounded to the nearest half foot, and then they mark their answer on the board, okay, their respective distance on the board with the remaining members of the class, okay? What do we do? Well, we want to use a one sample t-test to examine the theory that the average distance traveled for a paper airplane is larger than 7 feet, okay? So notice here that I give you a population average of 7, but down here, there is no standard deviation, okay? And again, it's really hard to find a population mean, and further, it would be hard to find a population standard deviation, okay? So this is not known, and what we'll have to do is an alternative method for a standard deviation in just a moment, okay? Your alpha cutoff is 0.05, and we'll address that in a little bit, okay? But how do we start this off? We start off the same way as before. We're gonna do step 1. We're gonna look at a null and an alternative hypothesis. Okay, and we'll start by writing our h sub 0 and h sub a. However, instead of writing p's, we're going to write mu. Okay, remember mu means average, and we are not going to use x bars to represent our null or alternative hypothesis. They're strictly mu's. Just like on the previous 9.2, we use population parameter representations with a p and not a p hat. Okay. Further, it also said that the class believed that the average length would be longer than 7 feet, and so I'll write that. Remember that your alternative will always be a less than sign, a greater than sign, or a not equal to sign. Okay. Up here, we like to make sure that those are equal to signs, and that's pretty much the way you see those designed for our class. Okay. We always define mu. The symbol here represented in our null and alternative hypothesis, and mu is the true population, mean number of feet a paper airplane can fly. All right, and again, it is the assumption that is 7 based off this website. Okay. All right, so step 1 is done. Our conditions are, our writing of the null and alternative hypothesis done. We will move on to our conditions based off our null and alternative hypothesis. And the first one is random. Okay, now disclaimer, this is something that we're going to look for in our work. Okay, but the bottom line I already told you is that this is my 4th hour. Okay, and so they're not random. I don't know if there's much bias in their paper airplanes that they created or then further tossed, but you know, they're a normal group of kids. But again, different people can make different airplanes, and maybe theirs was a little bit more unique compared to a traditional one. I'm not really sure. But the only way I could really do an experiment was by using my 4th hour. Okay, so is it random? It's really not, but I'm going to say look for this in your paragraph because it'll probably state it. Okay, and when they do, you want to identify that in your work. Okay. All right, second thing is your 10% rule. Remember, 10% rule means you take your little n. Now, some of you would wonder, is like, how many people were in your class? Okay, and I actually had 29. Okay, so 29 is less than or equal to 1/10. Well, basically, this is all paper airplanes. Okay, and so are there more than 290 airplanes made on this planet? Definitely, definitely so. All right, so that one's satisfied. Okay, the last one is the large counts. Okay, for normality. And again, I told you there was 29. So typically I ask, is your n bigger than or equal to 30 so that you can use the essential limit theorem? And unfortunately, our n is 1 short. Okay, so what we have to do is we have to take the data of the students from the class and their paper airplane distances, okay, as they were tossed, and we're going to look at it, okay, and evaluate it. And so here's what they are. They're listed all right here. There's all 29 of them. Let me just make sure I'm counting right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, so 29. And what am I going to do with this? Well, off to the left here, here's what I used to do. I used to make little X's, you know, with some scaling on the bottom. And you can still do that. We could do that here if we wanted. But because I oftentimes put data in my graphing calculator and I store things in my L1, I tried something just a little bit different, just to mix it up a little bit. And you're invited to do this as well. What I did is I made a box plot with all this. Okay, and so since all of these are stored in L1, and that's what I would encourage you to do, put those all in L1. What I did is this. I first went to my equation editor. I didn't really draw this where you have like y1 equals and then y2 equals and y3 equals. And just make sure they're blank. Make sure there's nothing in there. Okay. Once you clear out your equation editors, go to statplot. And statplot's the second button. And then I think the y is equal to. I'm pretty sure that's it. And you'll notice you'll get a screen that almost looks like this. It'll just say plot 1, plot 2, and you'll hit plot 1, and plot 1 will be highlighted. Okay, right here, and you want to make sure that you have on. Okay, and not only is it blinking on, but it's triggered. Okay, so you don't want the dark covering being over the off. You want to make sure it's on the on. Okay, and then you're going to want to go over to the 4th item here. So scroll down 1 and over, and that is a box plot that has outliers with it. Okay, so click on this guy, highlight it, and then make sure there is L1 in your X list. Okay, And then once you do that, what I do is this. To get a good picture, I hit zoom and then I hit 9. Okay, and if you're able to do that, you're going to get a picture that looks like this. Okay, now it's not enough just to look at the picture and say, yeah, it looks good, and then just mark that off. You need to recopy this onto your paper, just like you would make a graph over here to the left with your dots or your X's. Okay, so recopy this. Okay, and what's good for me is I like to put the values for your 5-number summary here, and they're already actually within the graph. So all you have to do is hit the trace button on the very top of your graphing calculator and then scroll left and right. And you'll find, like, for example, this is 3, this is 7, this is 9, 14.5, and 23. So I just want to give a little bit more perspective to my reader in terms of what those values are. And then decide first, do I have any large skewedness in this work? And I don't think I do. I don't have any strong skewedness. I have a little bit, but no strong skewedness. Okay, and do I have any outliers? I don't. If I did, you'd have those little dots. Okay, so no outliers. Okay, and so my conditions are satisfied even though I didn't have 30. Had I hit 30 in terms of my sample size, you could use central limit theorem to talk about a normal distribution, okay, or approximately normal distribution. All right, so those are my conditions. Again, you have to recopy this. You can't just say, yeah, the box plot I drew on my calculator had drawn said it was okay or showed that it was fine. You actually have to recreate it, okay, just like you would a graph down here on the bottom left. All right, third item. If you accept that, is we will move on to step 3. 1 and 2 are done, and we are going to first claim that the conditions are satisfied, which they are. We also put check marks for each one. Okay, we have one here, there, and again, it wasn't really random, but we're gonna assume that most research is. Okay, we're gonna move on to the test statistic. Okay, and that means you're gonna find your t, and in this case, here's what's happening. Your t distribution will follow this t-score that looks very similar to an item that you had in the past. Okay, the only difference is that instead of having p's and p hats, you have a mu in the back and you have an x bar in the front. Okay, so this is from your sample and this is from your population, your mu. Okay, further, notice I have no sigma. Okay, I do not have a population standard deviation. No population, I'm going to abbreviate that, standard deviation. And what does that mean? Well, if you don't have a population standard deviation, you're going to have to use your sample standard deviation. Okay, and when you divide by your square root of n, that combined is called a standard error. Okay, and we'll look at that in a second with respect to a picture. Okay, now I need a couple of things. First, I know that mu is 7 because that's what it says in my null and alternative hypothesis. And further, I know that my n is 29. Okay, and so what do I have to do? I'm going to have to plug in something for x bar, okay, and something for s sub x. And if I do this, you can see that I have an x bar, 11.21241, and I also have an s sub x, which is 6.045. Let me light those up here for you. Okay, and I'm going to plug those into my other 2 missing items for this t distribution, this t-score, if you want to call it that, and also identify what my degrees of freedom is. So I have 29 items, and in terms of people who participated in the study, 29 minus 1 is 28. All right, so as I put those in, I'm going to put that information off to the right here. Okay, and so I have my x bar minus the mean, okay, divided by the standard deviation over the square root of n. Okay, and I divided it out and I did some little calculations here. I did this division, I did that subtraction. This again is your standard error. I'm just going to put SE for now. And you divide that out, you get 3.778. Okay. And that is how many standard deviation our particular X bar is from the true mean. Okay. So we had an average that's about almost 3 3/4 standard deviations above the mean. Okay. All right. Now let me see if I have another picture here. Okay, we'll have to find the p-value. We'll do that in a second. I'm going to draw a normal curve here. And give you some perspective in terms of what we're going to find. Okay. Your population average is said to be 7. Your standard deviation is this right here. It's basically not standard deviation, it's your standard error, 1.1225. Okay, and I'm going to actually make this yellow so you can see it. Okay, and what I'm doing is I'm going to basically add that to the 7 here. So this actually becomes 8.1225. And my X bar, which is right here, is 11. And so 11, if I were to keep going, is way, 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 way out here. You know, I'll just approximate that. Okay, and I have to shade. And which way will I shade? Well, because my alternative says greater than, I'm actually going to shade to the right. Okay, what does that mean? I'm going to find the area or the probability of getting a mean as big as ours, okay, 11.241 from a sample of 29 or higher. When I say higher, meaning this average or an average that's higher. Okay. So what I'm going to do is I'm going to use this information to use a new command called tcdf. Okay, and I'll do that on the next slide. Okay, now, so for the p-value, we're onto a new screen. What I'm going to do is I'm going to use a calculator command called, again, tcdf, which I know I just talked about. And here's how you find it. Okay, what you're going to need is the t-score, okay, the value for t, the test statistic from the previous slide, 3.778, and again our degrees of freedom, which was 28. Okay, so your first slide will look like this, and you have to do second, and it's kind of like the hidden command, second distribution. Okay, and when you find that in your calculator, you're going to go straight to 6, and it'll say tcdf. Okay, and what you're going to do is you're going to do a lower bound. Okay, and in this case, because your picture, and I'm going to redraw it just kind of like this real quick, was a picture that looks something like this, where this boundary was your t, and it really travels to the right forever, okay, and I can't put infinity there. Your upper bound, we'll just pick a giant number for that, which we'll just say 1,000, okay? And then the final item they're going to ask for is degrees of freedom, okay? So let me show you what the screen will look like. And for some, it'll look like this, okay? This is your upper bound, lower bound, excuse me. Your upper bound is 1,000, and your degrees of freedom goes in the 3rd position, okay? And some of you have nice inputs where you just put them in like that. And that's how you represent a tcdf for a graph that travels to, has an area that travels on the right, okay? And so once you hit those in there, you'll get 3.797 times, remember E is really times 10 to the power of -4. Okay, so if you want to write this, okay, what this means is this is 3.797, I'll just say 8. It's right. No, that's not right. Let me fix that because that's mathematically wrong. okay, times 10 to the negative 4. Okay, so don't do this. Some people will just write 3.79. Okay, and they stop. They're like, here's my answer. And remember what you're talking about. This is a population. This is a proportion. Okay, so your proportions aren't bigger than 1. So the highest proportion you can have is 1. So 3.79 doesn't make sense. But if you include the tail of it, okay, then that does make sense. But don't put an E in your answer. That it's not proper to do that. That's not good calculator talk. You want to put times 10 to the negative 4. Or what I like to do is, again, make sense of this. What does this mean? Well, this times 10 to the negative 4 means that you're moving 4 place values to the left, okay? And then you'll fill those in with zeros. And so you basically have a value that's 0.000379, okay, or 0.0004. Either one of those is valid, okay? And I think I may have covered this up. We will see, but this is my p-value right there. Let's see where I got it. Oh, I didn't. Good. Now, you'll see that I have something just slightly different, okay? But this will round the same. This will still give you 0.0004, okay? So chances are I had this with my other class, and maybe there's some rounding issues because we did the actual t-test legitimately without using any type of rounding, okay? So, or sorry, with some rounding, and so that may be why it's slightly off, okay? All right, now that pretty much gives me my 4th step. That is my calculation. I'm now gonna want to write my final answer, okay? And so we'll write a conclusion for this, decide whether we reject or not reject, and it goes like this. Remember, because our p-value, which is super small, 0.0004, is less than my alpha cutoff of 0.05, okay, then we can write a statement like this, okay? Whenever your p-value is less than your alpha cutoff, that means you will reject the null, okay, because our p of 0.004 is less than our alpha cutoff of 0.05. I just restated that. And what does that mean? It means there is evidence to suggest that, and then remember that we write the HA, okay? And the HA says is that the average, true population average or mean, number of feet that a paper airplane can fly is, and then we'll look at this part, greater than 7 feet, okay? So again, whenever you reject something, you go right off to say there is evidence to suggest. If you did not reject, okay, because the p was actually greater than your alpha, then you would say there was no evidence to suggest, okay, just like before. Okay. Reminder that in this case also that we do not have to double our p-value, okay, because again, we do not have a two-sided test here where there is a not equal to sign where your HA is. Okay. All right, the last thing I'm going to do, and it's not something that is really part of my notes, but it was asked in the homework and it's asked on your AP test. And it'll say this, interpret your p-value. Meaning, what does p equals 0.0004 mean? Okay, and here's the idea, okay, and I'll try to put this up towards the top just so you can see this better. Now, we're going to take many, many samples of size n equals 29, okay, and with the millions of airplanes that have ever been made on the planet, if I just kept doing random samples of 29, I could get a lot of different X bars, okay? Now, most of them will hover around this mu is equal to 7, okay? Because if this is true, okay, if the population average truly is 7, most of my sample averages will also be around 7. Okay, and so if I did samples of size 29, okay, and took little averages for each of those samples of size 29, you're going to get a lot that have an X bar is equal to 7. You're going to have some that are a little bit bigger, just naturally, and some that will be a little bit smaller, but they should not be, if it's a full sampling distribution, be the same as the mu is equal to 7. Okay, you should have more exactly 7s, assuming that the null is true, than values that may be on average a little bit bigger or a little bit smaller. Okay, isn't it possible that you may get some more extreme sample averages? in either direction you can, but they won't be represented as high, okay? And again, these are just little dots that represent possible outcomes for samples of size 29 and their respective averages. And so if you did every single sample of size 29, you're going to get something that looks kind of like this, an approximately normal distribution. Okay. Now, in our specific case, our X bar was super far away. It was like way out here. Okay. And what we did is we put a boundary there and we shaded to the right. Okay. And we gave it what we called a p-value. Okay. And we're asking, what does that mean? Okay. So here's what it means. And I'll put my definition on the bottom down here. It means this: assuming the null is true. Okay, that, and I'll just put this in parentheses, that the average length of a paper airplane's distance once it's tossed is 7 feet. Okay. The probability of obtaining sorry, that's messy. Let me fix that. The probability of obtaining a sample average as large as ours, okay, which is what, I'm going to go back to the top, which is what this dot was, okay, this point, that cutoff, or higher, and I say or higher because I'm traveling to the right, okay, is, and then that's your p-value, 0.0004. Okay, so yeah, was it common that we got an average that was as high as R, assuming that this null is true? No, it doesn't happen very often. Okay, it's the probability is 0.0004, which makes me wonder if this average of 7 feet for the population is really true. Okay, but they will ask you, I'll even say this, it'll be on my test, to interpret the p-value. And that doesn't mean write a good conclusion. Okay, it's not what you see right here that I'm kind of putting a brace around. Okay, this is important information. That's a conclusion about your hypothesis test. When I say interpret the p-value, what I'm saying here is, what does this really mean? Okay, not what is it a detail for in terms of answering the question. What does this calculation really stand for? Okay, and again, it's the assumption that the null is true. It's the probability that we got a sample average, okay, as unique as ours, or even more unique, in this case, in the positive direction. And we acknowledge that that probability is 0.004. Okay? All right, so take note of that. You will see that again. All right. Now, while we did a greater than sign, okay, we had a moment where we had our alternative that was greater than. Know that I could give you another one similar to this where you have a less than sign for a different type of problem. So you can have not equal to signs where you have to double your p-value, assuming you're not using your calculator. But this work is exactly like the one that you did in 9.2. Okay, the only difference is that you're dealing with averages as opposed to proportions. All right, now one more thing, okay, and it's a second problem, but it's a little bit different than the one that we're doing now, okay, and it's called, oh, let me show you the calculator way, sorry. This is called the tcdf way of doing this, and this is actually a fast way, okay? So this helps replace step 3 and 4. I forgot I had this for you, okay? Now, I know you had your tcdf, okay, and that's kind of nice, but if all of your items are in L1, okay, and I'm just going to circle that L1. If everything is in L1, here's what you could do. You did this to your tcdf way, okay, and that's certainly helpful. It made us use our equation, helped us really draw a good picture actually too, okay, with respect to our normal curve and cutoffs and shading, okay. But if you would like a quicker version to get steps 3 and 4, okay, then what you'll do is you'll write this. I'll put this command right above the screen. You're going to go to stats. you're going to scroll over to calc and go to tests. Okay, and notice what you have here. It's tests, it's highlighted. Okay, and instead of going to 5, which you did in 9.2, okay, you're going to go to ttest here, which is this guy right here. This is 9.3. Okay, and then from here, you're going to click on it. You're going to click 2. Okay, all of your data happens to be in L1, so you don't have to really do anything further. I've addressed that in the list we're using L1. You put the sample average of 7. Make sure you pick the right inequality. This has to match the HA, and that is a greater than sign, just as you see right there in the HA. And if you go down and calculate and click that, you notice that you got something similar to what we had before. Okay, and notice that this, okay, is nearly the same. Okay, the fact that we have to put rounded values into our tcdf means that it won't be exactly the same, but it's sure darn close. Okay, this includes the entire t. When they do the calculation, we had to stop after 3 place values. Okay, so if you want to do this again for step 3 and 4, you may do that.